In this video, we're going to discuss the inverse of a matrix. Let's recall from section 6.3 what the identity matrix represents. So we'll write that as I, and it's got ones along the main diagonal and zeros everywhere else. So the 2 by 2 identity matrix looks like this. If we were talking about 3 by 3 matrices, then we would say the identity matrix looks like this. So again, it would have ones along the main diagonal from the top left to the bottom right, and it would have zeros everywhere else. So that's our 3 by 3 identity matrix. Now let's get into our main definition for this video. Let's start with a square matrix A. So imagine that A is 2 by 2, 3 by 3, etc. We're going to define a matrix called A to the negative 1. And A to the negative 1 has the property that when you take A and multiply it times A to the negative 1, you get the identity matrix. And this is also true if you do your multiplication in the other order. So A to the negative 1 times A is equal to the identity matrix. So this matrix, A to the negative 1, that makes these two highlighted equations true, is called the inverse of A, or it's sometimes called A inverse. So often you'll hear us say A inverse for short. So one thing to be aware of is that some square matrices don't have an inverse, and we'll see in a minute how we can figure out which square matrices do have an inverse and which ones don't have an inverse. If a matrix is not square, then it certainly does not have an inverse. So here's a 2 by 2 matrix A, and we want to check that this given matrix here, 9, 4, 2, 1, we want to check that that is equal to A inverse. So to solve this type of problem, here's what we need to do. We can check that A inverse times A equals the identity matrix, or we can check this the other way around. We can go A times A inverse equals the identity matrix, and you only need to check one of these, because it turns out that if one of the equations is satisfied, then the other one is automatically satisfied. So it's up to you in terms of which equation you prefer. I think I'll start with this one here and just check that A inverse times A really does equal the identity matrix. I'm just going to start with the left side. Take our A inverse times A. So that's 9, 4, 2, 1. We want to multiply that by our matrix A, 1, negative 4, negative 2, 9. And we're just going to multiply this out in the usual way. And if we get the identity matrix, then we're done. So we'll circle the rows of our first matrix, columns of our second matrix, and just do our usual dot product operation. So we're going to have 9 minus 8 is 1. Negative 36 plus 36 is 0. And we've got 2 minus 2 is 0. And then negative 8 plus 9 gives us 1. So yeah, sure enough, that does equal the identity matrix. So that's how we know that this highlighted matrix here really is the inverse of the matrix A that we were given in the question. So now we're going to work towards finding a formula for A inverse. Before we can do that, we're just going to look at a quick definition. So let's say we have a matrix A, 2 by 2 matrix A, that looks like A, B, C, D, and we want to define something called the determinant of A. So for short, in notation, we're going to call that capital D. The determinant of A is just a specific number. It's the number that you get if you multiply the forwards diagonal and then go minus the product of the backwards diagonal. So you go A times D minus B times C. So that gives you some number, and that's called the determinant of A. So now we're going to write down a formula for the inverse of A, and we'll see that involves the determinant. So to find the inverse of a matrix A, you're going to go 1 over the determinant, and then you're going to multiply that by a modified matrix. So let's take a look at what's inside this matrix. So notice that the diagonal entries have swapped position. So the D and the A have swapped, and the off diagonal, the B and the C, have had their signs changed. So that's the formula for finding the inverse of a 2 by 2 matrix. So we'll do some practice with that formula in a minute. So a couple of comments about this. If the determinant is equal to 0, then A inverse does not exist. So that tells us exactly when our matrix will not have an inverse. And I would also point out that the formula only works for 2 by 2 matrices. If we ever run into a situation where we need an inverse for a 3 by 3 matrix, we'll see a method a little bit later on for how to do that. So we'll only be applying this particular formula to a 2 by 2 matrix. So we're going to try a couple examples of applying that formula. So the question says, find A inverse for the following matrix A. Okay, first thing we're going to do is calculate the determinant of A. So we'll just call that capital D so that we're giving a name to it. We're going to multiply the main diagonal, so the -5 times the 1, and then we subtracting off the product of the backwards diagonal. So minus -2 times 2. And we just work out what this number is. So -5 plus 4 gives us -1. So that's our determinant. Okay, now I'm going to write down the formula for A inverse. So we're going to go 1 over the determinant times, and now we're going to change some of the entries of our matrix A. So we're going to swap the diagonal entries, and we're going to change the signs of the off-diagonal entries. So this is going to look like 1 over -1. The -5 and the 1 are going to change position, and the off-diagonal entries are going to get their signs changed. So this -2 is going to become a +2, and this 2 here is going to become a -2. So we could leave it like that, or we could say 1 over -1 is the same thing as -1. So then we could multiply that -1 all the way through the matrix, and that would give us -1, -2, +2, 5, and that's our A inverse. So let's try a second example like that. Let's find A inverse for the following matrix A. So first thing we would do is calculate the determinant. We're going to multiply along the main diagonal, so 1 times 6, and then we're going to subtract off the product of the other two numbers. So subtracting off 2 times 3. So 6 minus 6 is 0, and as soon as we see that that determinant comes out to 0, we can say A inverse does not exist. So the reason that happens is because if you apply the formula for A inverse, you're going to be dividing by that determinant, and we know that dividing by 0 is undefined. So that's why a determinant of 0 immediately leads us to the fact that A inverse does not exist. So let's recall another fact. This is back to our previous section, section 6.3. So if we take a system of equations, let's say, for example, this system of equations here, we can write that as a matrix equation in the following way. So we would pull the coefficients out of the system. We'd have 1, 2, 3, 4. We can pull the variables out of the system. We write those in the column, in the form of a column. So we'd write x, y, and then we can pull the constants from the right side of the system, the 7, 15. We write those in a column. So that's the matrix version of that system, what's often called a matrix equation. And if we wanted to write that symbolically, where we don't really care about the specific numbers, but we just wanted to talk about the system as a whole, the way we wrote that in section 6.3 was just AX equal B. So this equation AX equal B represents a system of equations. So now we can talk about why do we care about the inverse of a matrix? Well, suppose we want to solve a system of equations. And rather than writing the system out the long way, I'm just going to write it the symbolic way, AX equal B. So suppose we want to solve that. Well, let's say that we know that A inverse exists. Then what we could do is multiply both sides here by A inverse. And we know that A inverse times A gives us the identity matrix. So now what we've got on the left side is IX. And remember from section 6.3 that if you multiply I times any matrix, you just get that matrix back again. So what we would have on the left side is X. And so this formula collapses to X equals A inverse times B. And that's really nice because what that's doing is that's giving us the solution to the system. Because remember, X is just a little matrix with a single column here that contains our variables. And so if we actually multiplied on the right side, if we multiplied A inverse times B, what we'd get is some number, some other number, and those numbers would be giving us the values of X and Y. So the reason why we care about the inverse matrix is that it gives us a really fast way of solving systems. Right, so let's write this fact up in words. A system of equations, ax equal b, has solution x equal a inverse times b, and that will work anytime a inverse exists. So I'm just going to put a star beside this little formula here, x equal a inverse times b, and we're going to apply that in our next example. So here's the classic type of problem for this section. It's going to ask us to solve the following system of equations by finding a inverse. So first thing we should do is just pick out our coefficient matrix from the problem. So pulling out the coefficients in the order they're written, 7, -3, 2, 1. So that's our matrix A. Now what we're going to do is try to find the inverse of this matrix. So let's think about finding the determinant of A. We go forwards product, 7 times 1, minus the backwards product. So minus the -3 times 2. If you want to think of this in terms of muscle memory, I just think multiply these and then go minus that product there. Okay, so let's work out this number. It's 7 plus 6 is 13. So that's the determinant of A. So let's think about our formula for A inverse then. We're going to go 1 over the determinant times a modified matrix. We're going to be swapping the diagonal entries and changing the sign of the off-diagonal entries. So if we fill this in, this is going to look like 1 over 13. Okay, now let's change the entries that were on the diagonal. So the 1 and the 7 are changing positions. And then the entries that were not on the diagonal just get their signs changed. So the -3 becomes a +3, 2 becomes a -2. And that's our matrix A inverse. So now that we've gotten that, we're going to finish off the problem by saying x equal A inverse times B. So this is the reason why we care about the inverse matrix, is that it gives us a fast way of solving a system of equations. So let's fill everything in here. So x is a column matrix that represents our variables. We've got A inverse that we just figured out. So 1 over 13 times 1, 3, -2, 7. And then that gets multiplied by this matrix B. So let's think back to section 6.3, where we were writing down systems of equations. B is a column matrix that represents your constants. So if we go back to the original system in the problem, just look at the numbers that are on the right side. It's 25 and 9. So those are the numbers that go into the matrix B, and again, always written in the form of a column. So the idea is that if we can just do this multiplication on the right side, then we can figure out the values of x and y, and we'll be done. So the matrix xy equals, we'll leave the 1 over 13 hanging out in front for now. We're going to circle any rows of our first matrix and any columns of our second matrix, and we're going to do our usual matrix multiplication now. So we've got 25 plus 27 is 52, and then we've got -50 plus 63 is 13. Okay, and then one last step to get some nice numbers here. Anytime you have a number sitting in front of a matrix, you can just multiply that number through. So this is like saying we've got 52 over 13 and 13 over 13, except that those fractions reduce to nice numbers. So 52 over 13 is 4, and 13 over 13 is 1. So that's giving us the value of x and y. If you write this down another way, say the ordered pair xy is 4, 1. And you can go back to your original system and just confirm that really does satisfy both equations. So we know we've done that correctly. So we talked about how to find the inverse of a 2x2 matrix. And we also saw how to use that inverse matrix to solve systems of equations. So that's our video on the inverse of a matrix. Thanks for watching.